Hello, everyone. My name is Dr. Kate Bulinski. I'm an associate professor of geoscience at Bellarmine University, and this presentation is a small overview, a short overview of some of the basics of the science of climate change. So I'm hoping that with this brief introduction, you'll get a better appreciation for what we know about climate change and global warming and some of the connections between the two topics. I'd like to start this presentation with a definition of what global warming is. It is very simple. It is an increase in the average temperature of the globe. And this graph depicts what we're talking about very nicely. This is a graph from the National Oceanographic and Atmospheric Administration showing the temperature record from 1880 to the present day using high quality records using thermometers. It's compared against the baseline of the 20th century average, so you can see that there's been quite a bit of warming over the last 150 years or so. So we can see that global warming is something that we can measure with thermometers on our planet today. To follow that, we can definitively say that the world has warmed. The planet is about 2 degrees Fahrenheit or a little more than 1 degree Celsius warmer than the baseline beginning in 1880 to 1910. And that's based on lots of different kinds of records using thermometers worldwide, looking at ocean records and land records. If we look at the more recent record, we can see that since 1880, the warmest decade on record was 2000 to 2009, and we are slated to see the most recent decade, the one that we're currently finishing up, being even warmer than that. If we look at the 10 warmest records since 1880, the warmest years on record, you can see that most of them have happened within the last couple of decades, and the last 5 years have also been the hottest 5 years on record. So we are seeing quite a bit of a different global temperature range than we have in the 20th century or the centuries before that. So to follow that, we want to talk about what climate change is as well. Just to note that a lot of people actually confuse these two terms or use them interchangeably, but they're actually different. Climate change is a change in the distribution of weather patterns over time, and it is a change in the temperature of our planet that causes climate changes. So global warming can cause climate changes, but also global cooling. We've seen this in the geologic record that there have been many cold periods and warm periods in the past, and climate changes as a result. So I'll come back to that a little bit later about some of the patterns we've seen in the geologic record, but just acknowledge that we have changes in temperature on our planet that drive changes in our weather patterns. The most well-known cause of global warming is known as the greenhouse effect. This effect works when some gases in our atmosphere act to hold in and trap heat and essentially warm the atmosphere. So you can think of them as like a blanket. They're a blanket that's sort of holding heat in our Earth, and the source of the heat is the sun. It's transmitting some of its energy, and some of it bounces around in our atmosphere and warms our planet. The most common greenhouse gases are listed here. I have them divided into kind of two separate categories. So there's carbon dioxide, methane, nitrous oxide, and chlorofluorocarbons. I'll talk about each one of those individually, but those are the greenhouse gases we tend to track in terms of the amount of emissions that we see entering into our atmosphere. There's also ozone and water vapor. Those are also greenhouse gases. They do trap heat, but they function a little bit differently. So I will discuss them at the end of the discussion about these greenhouse gases because they are just a little bit different. First, we'll start with carbon dioxide. That's the greenhouse gas we hear about the most in the news and just in the general discussion about climate change. We hear about it a lot because it is the most abundant greenhouse gas. A few other things to know. When carbon dioxide is released into the atmosphere, it doesn't dissipate right away. It actually stays up in the atmosphere for a while, somewhere between 50 to 200 years. So that means that increases in carbon dioxide that are going into our atmosphere now will have an effect for at least 50 years and likely longer. There are some human-caused sources of carbon dioxide in our atmosphere. Burning fossil fuels is one. One that we don't hear about very much, but is actually a very important source, is from the cement industry. When we make cement, we take calcium carbonate, like limestone, and we heat it up, and it turns into lime, which is calcium oxide, and then it releases carbon dioxide directly as a gas into our atmosphere. So you think about the cement that we use all around the world and the amount of cement that we need, we're releasing quite a lot of CO2 that way as well. There's also a release of CO2 through deforestation as we're cutting down and burning trees, and we have less trees photosynthesizing and pulling in carbon dioxide. So these are some of the major sources, and you can see in that graph there some of the sources in the United States: electricity generation, transportation, industry, heating and cooling, etc. Methane is another powerful greenhouse gas. It's actually more powerful than CO2. So if you compare one molecule of methane to one molecule of CO2, it acts like a thicker blanket, a warmer blanket. It stays up in the atmosphere for less time though, about 12 years. The main sources are agriculture, landfills, some industry. Also, as the world is warming, the permafrost and the oceans are releasing methane. We also release it when we're drilling for oil and gas, and then some livestock emits it as well. So cows release methane through their digestive system, and there's more than 1 billion cows on the planet. So that's a sizable amount of methane that's released. If you look at the United States emission sources, you can see that fossil fuel industry through natural gas and petroleum systems is part of it. The enteric fermentation on the screen is referring to the cow digestion. Then there's landfills, manure management, coal mining, and some other sources too. Nitrous oxide is a very powerful greenhouse gas, almost 300 times more powerful than CO2 when you compare the two molecules to each other. It stays up in the atmosphere for a long time as well. It's just much less abundant than CO2, so there's a smaller percentage of nitrous oxide, just as very powerful. This is generated somewhat from burning fossil fuels, somewhat from industry, but the biggest source is actually through agricultural processes. When we are applying lots of nitrogen fertilizers to the land, some of that nitrogen actually is released to the atmosphere as nitrous oxide. And so the soil management through our agricultural practices is the largest source of nitrous oxide. But we also look at manure management and industrial processes and transportation as sources. Chlorofluorocarbons, which are known as CFCs, and a related set of compounds, hydrochlorofluorocarbons, are synthetic gases that are used in industry primarily for refrigerants and also for propellants and aerosol cans. And they are very powerful greenhouse gases, thousands of times more powerful than CO2, and they can stay up in the atmosphere as long as 50,000 years. It just depends on which compound you're talking about. They are best known for a separate environmental problem, which is the destruction of the ozone layer. So the ozone layer in the atmosphere protects us from ultraviolet radiation. And a few decades ago, scientists discovered that these chemicals were actually breaking down that ozone layer. So as a result, there were international agreements to phase out the use of CFCs so that we could halt the destruction of the ozone layer. And the CFCs were replaced with a related set of compounds called hydrochlorofluorocarbons. They don't have the same effect on the ozone layer, so they're considered safer in that respect. But both CFCs and HCFCs are very powerful greenhouse gases. Now, HCFCs will also be phased out. There are plans for them to be completely eliminated by 2030. So as you can see in the pie graph below, these are synthetic compounds, so they are produced through industrial processes. Now, a few words about those two greenhouse gases I mentioned that function a little bit differently, ozone and then water vapor. We'll start with ozone. So ozone actually functions different ways in different parts of the atmosphere. So there are parts of the atmosphere where ozone is good, and there's parts of the atmosphere where ozone is bad. So we'll start at the bottom of this picture here on this slide. if you look at the bottom, ozone is actually harmful towards the surface. So on days when it's really hot in the summer and there's a lot of pollution, you may sometimes hear about ozone alert days. Those are days when people with asthma or other kinds of breathing problems are told that they should probably stay indoors because there's a lot of pollution in the air, and it's this ozone from mostly cars and trucks on the road that are causing a problem. So that's where ozone is bad. If we go up a little higher in the atmosphere into a layer called the troposphere, this is where ozone actually can be good. It chemically reacts with pollutants and will break it down. So there, ozone can be helpful chemically. If we go up a bit higher, we get into a zone where ozone is bad in that it is a greenhouse gas. So that is the layer when we're talking about the climate system when ozone has the biggest effect. If we go up into the highest levels of the atmosphere up here, this is where ozone is the ozone layer and where it actually will absorb ultraviolet light from the sun and protect us from the radiation from the sun. And so that's the layer where the chlorofluorocarbons are breaking down the ozone layer. So you can see here that ozone actually functions differently. So it's not such a simple answer about what ozone does in the atmosphere. Now, water vapor is technically a greenhouse gas. When temperature on the planet increases, there's more evaporation of water, and the water vapor traps heat like a blanket, just like other greenhouse gases. On the other hand, water vapor forms clouds, and the white clouds up in the atmosphere actually reflect some solar energy back to space. The white color actually bounces that energy back. So water actually both traps heat and reflects it. So there's a bit of different feedback loops at work here. As the planet is warming and adding more water vapor to the atmosphere, we have both the effect of trapping heat and reflecting it. So it is, again, not as straightforward to understand as some of the other greenhouse gases. A little overview about the greenhouse gases in the United States. So on the left-hand pie chart, you can see the major greenhouse gases and their proportions as emitted by the United States. This is the most recent data from the EPA in 2016. And 81% of the greenhouse gases from the US are carbon dioxide. So that's why we talk about it the most. It's the most abundant greenhouse gas. 10% is methane, 6% nitrous oxide, and 3% are those CFCs and HCFCs. The other two, ozone and water vapor, are not usually tracked in the same way. And then if we look at the parts of the economic sector that are responsible for greenhouse gas emissions in the United States, you can see the main sectors are transportation, electricity generation, industry, commercial and residential activity, and agriculture. So if we want to change anything about greenhouse gas emissions, those are the sectors of our economy that we'd want to pay attention to. If we look at a global picture of greenhouse gas emissions, they look a little bit different. So the pie chart on the left is the types of greenhouse gases that are emitted. And note that carbon dioxide is the most abundant, and they divide it up into two different categories. There's fossil fuel and industrial processes, and then there's a category for forestry and land use. And then you can see the other greenhouse gases broken down there. On the right are the different sectors that are responsible. So the main difference between what the United States is emitting versus the world is that we see this big shift with land use and forestry and agriculture. So on a global scale, there's a lot of changes happening with deforestation and the way that we're conducting our agricultural practices that are having a global effect. Another thing to know about what we know about the Earth climate system is that the greenhouse gases that we see in the atmosphere have a particular amount of certain kinds of carbon. Right now, the atmosphere contains more carbon-12 than you would naturally expect to have in the atmosphere. And that's because fossil fuels contain higher proportions of carbon-12. They formed from dead plants, and plants contain more C12 than other forms of carbon. And so when you burn fossil fuels, you're putting extra C12 in the atmosphere. So that's like a little fingerprint that tells us where the extra CO2 in the atmosphere is coming from. It's coming from that burning of fossil fuels, what's releasing that C12 in higher amounts in our atmosphere. So I want to talk about what else affects the climate besides the greenhouse effect. So I've mostly talked about greenhouse gas emissions, but there are some other processes at work too. So the Earth moves in space in an orbit around the sun, and you may have been taught in school that it's a circular orbit, but it actually varies over time. There's a circular orbit that goes to an oval orbit and back again, which is the eccentricity of our orbit. The Earth actually tilts more and a little bit less over time, which is obliquity, and it has a bit of a wobble, which is the precession. So the Earth actually moves in space in these different cycles. And long story short, that changes the amount of energy we get from the sun over time in a cyclical pattern. And we can look at this pattern over the last million years or so of Earth history and see that it has driven big changes in our climate. Hot periods and cold periods, or glacial cycles. So you can see that in the bottom of this image here. This is actual data from our hot periods and our cold periods on our planet. So Earth's orbit and cycles of the sun combine together to cause natural cycles of climate change. And we've seen this for the last several million years on our planet, at least. Another factor that has an impact on our planet is what volcanoes are doing. So in recent times, volcanic eruptions that we have on the Earth have contributed to episodes of short-term global cooling. The ash that's emitted by these really large volcanoes goes up into the atmosphere and reflects some energy from the sun back out to space, which cools the planet for a little while until the ash filters out of the atmosphere. So that's what this graph is showing. You can see the y-axis here is the temperature of the planet in terms of the average land temperature, and then we have the year here on the x-axis, and this is the temperature increase over time. And there's these big dips in places, and these are very large historic volcanic eruptions. So you might have heard of, for example, Krakatoa as a very famous example. There's also Mount Pinatubo from the Philippines that erupted very explosively in 1991. And these actually caused a global dip in temperature of a degree or two for a year or two until the ash filtered out. Now, looking into ancient geologic records, there are different kinds of volcanic eruptions that have happened in the past, and they're called flood basalt eruptions. They are linked to past episodes of global warming because those kinds of eruptions release lots of greenhouse gases. But we haven't seen any eruptions like that for many millions of years. So those are not the kinds of eruptions that are happening today, and they're not contributing to our pattern of global warming in any significant way. So how do we know what we know about ancient temperatures? We often compare what's happening today to what's happened in the past, but where do we get that information? So I want to start going back to that first graph I showed you with global temperature since 1880. These are measured with thermometers. So we understand that these are direct observations in real time of our temperature. There's actually other sources of data that can help us understand the temperatures of the past. One is data from ice cores. So when scientists go to study glaciers around the world, whether those are mountain glaciers or the very, very thick ice sheets, they can go to these ice sheets and glaciers and core down into them and pull out like big plugs of ice. Glaciers are laid down sort of like layers of ice, sort of like tree rings. And the oldest layers are on the bottom, and then they stack one on top of the next. So we can actually look at the thickness of the layers and some of the chemical composition of the layers to tell us some things about our past climate. But the most valuable source of information of all from these ice cores are little trapped bubbles of air. So the picture on the bottom there is a slice from an ice core, and it's full of bubbles. So when that ice was forming many thousands of years ago, there's little tiny capsules of ancient air that's trapped in the ice. So it's like a little time machine that tells us exactly what the greenhouse gas composition of the atmosphere was like when that ice was forming. And since the glaciers form annually with these layers stacking one on top of the next, we can look at how the atmosphere changes through time. So this is a very complete record of what ancient atmosphere looked like. So here's a graph that goes back not just till 1880, but actually going back to the year 1000 AD. And it's compared to the 1961-1990 average. That's the line that you see going through the middle of the graph here. And you can see a few things. One is that we have this line that's wiggling around here, the slight decline. This is the historic record that's based on several sources of data. We have data from ice cores, from tree rings, and also from corals. You can get isotopic records from corals. And those sources of data together give us a picture of what our temperature was over the last 1,000 years or so. And then when you add in the temperature record from thermometers, that's the red line that continues here, and that's the more recent record. So this is a graph that's showing something is different is happening since, say, the mid-19th century on. So that's our first little inkling, at least in this lecture, that something is different than the past records from before, say, the Industrial Revolution. Something very different is happening. We can go back even further. So Antarctica has ice sheets that are 2 miles thick, and so you can go back a very long way with climate records. These graphs show 800,000 years of data. So there's two curves. One is the CO2 concentration, that's the blue curve here, and then we have the temperature for Antarctica that's built off of these records, and it goes up and down more or less in sync. So when CO2 is higher, temperature is higher. When CO2 is lower, temperature is lower. And we can see that it goes up and down over time, and that's that cyclicity of ice ages and warmer periods that are driven by those changes in the orbit that I talked about earlier. Now what's different is if we put on the information from today, from more recent time periods, from thermometers, we can see that it has gone up above the scale on this slide. So you can see at the bottom it says as of January 2019, according to NOAA, our current concentration of CO2 in the atmosphere is over 410 parts per million. So we have, in a geological blink of an eye, gone much higher than we've seen in the last 800,000 years of geologic time. So there's something really is distinctly different happening here. I'll also point out that greenhouse gases concentrations have increased very quickly. These are records from the last 10,000 years, and you can see that the most recent record shows a spike in carbon dioxide, in methane, and nitrous oxide. So all three of those greenhouse gases are increasing very, very quickly in very recent times. So something distinctly different is happening with our concentration of greenhouse gases in the atmosphere. We can also go back even further than that and look at ancient climate and temperature in deep time. And that's with using different kinds of isotopes, in particular oxygen isotopes. I'm not going to explain it in a whole lot of detail right now, but I do want to mention that the climate on our planet has always been changing. We've had very warm periods in, say, the time of the dinosaurs, for example, very cool periods in, the Ordovician ice ages, and some of these kinds of big shifts in temperature have been associated with mass extinctions events. So there's all kinds of interesting information we can glean from the fossil record and the geologic record to understand how our Earth system works and how the climate of our planet works. What's different is that our episode of current climate change is extremely rapid. It's virtually instantaneous in the geologic sense. So it's something that is really unprecedented. When we look at a record like what's on this screen here, this top part is the present day, and going back millions of years, so back 65 million years back into the time of the dinosaurs at the bottom of the scale, we can see that the temperature goes higher and lower over time, but then it's the most recent record that is spiking essentially instantaneously. So I introduce this here just to say that we don't expect our climate to be static, to be staying the same all the time. We know that the Earth system has changed lots over the past, but what's happening today is different, is rapid, and should not be ignored. All right, thank you.